Am I audible clearly? Okay.
Yeah, audible.
Yeah. So my slides are visible. I have shared the slides.
Yes, it is visible.
Okay. So in case of no, you are unable to see the slides, or my voice is not coming. So one of you kindly interrupt. Okay. So
Okay.
when Dr. Rabul contacted me and about this event and asked me to give an invited talk, of course, working in the speech processing area and seeing the changes that are happening in this area for about 2 decades, I thought it is more appropriate to briefly highlight the nuances of using deep learning approaches in speech processing. Of course, last 1 decade or so, the terminologies like artificial intelligence and deep learning have swept across many disciplines. Speech is no exception. I can say speech processing is one area where, after image processing and computer vision, the next area which picked up is deep learning in the earlier trends itself. So accordingly, it may be good to appreciate what was there before these deep learning approaches came into the field, how researchers in the speech processing area were trying different attempts to improve the technologies that were there. Then with the entry of deep learning into this field, how it has changed the domain. So that will be the scope of this talk. I'll briefly mention about the speech processing area. Then I will give, actually before looking into how deep learning is exploited in speech processing, I will give a brief overview about the deep learning, because now the deep learning approaches are not only limited to speech processing, it is becoming day by day all pervasive in all fields, all walks of life, including science, engineering, medicine, management. Every field people started using it. It may be a good idea to get a general feel about this artificial intelligence, pattern recognition, machine learning, and deep learning. Before this deep learning came into the speech processing area, the approaches that were prevalent in the speech processing area may be grouped under what is called speech processing by pattern recognition and machine learning. After that, the recent one is speech processing by deep learning, these deep learning networks approaches. Of course, there are many literatures, many works that have been done last 1 decade by using deep learning in the speech processing area. I will not cover any of them. Only I will take one basic landmark work, what is called acoustic modeling using deep learning. I'll illustrate in the sense, not illustration. I'll take the result from the literature and explain that how was the field or performance of the acoustic modeling or phoneme recognition system before this deep learning came into the domain, and after this deep learning came into the field, how the performance has changed. And that was one of the cornerstones of pushing this deep learning framework into speech processing area. After that, it entered into all sorts of fields like speaker recognition, language identification, emotion recognition, name it. Any task you take, people explore these deep learning framework. And I'll summarize my talk. Of course, when you come to the speech processing area, this is of course, electrical communication, electrical aspect of speech processing may be viewed as, once the computing machines or computers entered into the academic scenario, people have dreamt of developing computing machines that can recognize the speech and generate speech as early as early 1950s. Okay. From there, the interest was there for the research community as an alternative mode of using keyboard and joystick and other visual display input-output devices. Can I use speech as a mode of communicating with the computing machines? That is where the curiosity has grown in the researchers, and researchers started working in that direction, realizing this dream as early as 1950s. Of course, many developments took place. Um, Whenever the technologies, new trends came, people are able to demonstrate the proof of concept that we are able to get a demo system for recognizing the speech, or demo system for generating the speech for the computing from the computing machines. However, these technologies remained as demonstration systems in a controlled environment. They were not commercially successful. For the last 1 decade or so, you are hearing about a lot of speech products in the market, as more specifically speech recognition. To name a few, like Amazon Alexa, Google Speech, IBM Watson, Apple Siri, Microsoft Cortana, etc. These are just examples to illustrate. Essentially, it caught the attention of the community, and the speech recognition technology migrated from the lab to the field. So now you can see in the TV advertisements or something, you see Amazon Alexa device in the home. Persons can just speak to it like your friend, and it will recognize what you want, and accordingly it will initiate the action in that direction. Of course, now it has gone into other devices, even vehicles and all those things, the speech recognition aspect. One of the main reasons that is attributed for this commercial success is the significant improvement in the performance of the system that is achieved by using deep learning. Of course, when I take this deep learning framework, researchers in the neural networks field thought about deep learning long back, before this wave of deep learning came into picture. But at that point, the time was not ripe. But in the last 1 decade or so, it became very fertile ground for deep learning models to flourish. That is, the success of deep learning in this last 1 decade can be attributed to the timeliness of computing infrastructures like GPUs. Also, a huge heap of digital data that is available for processing. You take any task. Just to give an example, in the speech processing area, earlier when we want to develop a speech recognition system, collecting few hours of speech was a struggle. We used to spend months together in the laboratory for collecting and organizing this data. But nowadays, with this connected world globally through the internet, with many voice-enabled applications available on internet, so as a result of that, millions of hours of digital speech data is available on the internet, which people can utilize. I'm sorry, just power went. So millions of hours of speech data, digital speech data available at disposal. Both these aspects. One is very high capability computing infrastructure enabled by GPUs, and a huge heap of digital data available for processing at disposal. It enabled a fertile ground for training technologies, or specifically speech technologies, using such a huge amount of speech data. We can crunch them using GPUs available. Accordingly, these big models proposed in the deep learning framework can indeed be successfully trained to capture good information from the speech area. Okay, so that is the success that has resulted in commercially successful speech technologies. If any of you have any doubt, kindly interrupt me while during the talk itself. Ashraf, am I audible? Hello?
Yes, sir, you are audible.
Yeah, because this is one-sided, no, that's where
Yes,
And
yes, yes.
yeah. So now, for example, if I come to the field of deep learning, um, there are these four terminologies: artificial intelligence, pattern recognition, machine learning, and deep learning, being used interchangeably or more often when community nowadays discuss. If you view all of these terminologies, it is better to understand the relation among these four terminologies. Of course, if you consider artificial intelligence, it is not that even though it is extensively talked about even in commercial sectors like industries about this artificial intelligence in the last decade, but this artificial intelligence terminology came much earlier, where people grouped all those attempts that have been made to enable computers to perform intelligent tasks. And that field was termed as artificial intelligence. We will see in the next following slides about what is meant by an intelligent task. But all those attempts, research attempts that have been made to enable computers to perform intelligent tasks are viewed under artificial intelligence field. Of course, as one of the directions subfield in the artificial intelligence, they observed that specifically when it comes to the task humans handle, like recognizing speech or generating speech or recognizing an image, recognizing some temporal event happening, people found that that approach employed by humans is quite different compared to what is being employed in a computing machine. In computing machine, it is based on Van Neumann architecture, stored program concept. You store the data to be processed, you store the program to be processed, and the program is nothing but an ambiguous set of instructions. So using that, so the program, if it is written properly, it will take that input data and follows sequence of steps dictated in the program and crunch those numbers, produce the output. Whereas when you come for humans, when they deal with the information that is fed to them via their sensory mechanisms, for example, auditory sensing system, visual sensing system, touch, smell, or other mechanisms, whatever sensory mechanisms we have, there humans have, our cognitive system has evolved an approach which tries to look for something which is distinct, which enable it to store that information and use that knowledge later when such a scenario occurs once again, use that knowledge to deal with such a situation which has occurred earlier, and now based on that learned knowledge and that uniqueness what they're going to search is given a name what is called patterns. So thus humans, when they deal with external world using these sensory mechanisms, they always look for patterns present in those information that is being accessed through these sensory mechanisms. Then they felt that, oh, if we want to make these computing machines to handle speech or visual data or any other sensory data, we want to feed it to the computer, and the computer wants to mimic how humans are dealing with that. Then we have to evolve this approach motivated by this way of visualizing patterns instead of data. That is where this pattern recognition field came within that broader picture of artificial intelligence. That pattern recognition essentially, again, describes those approaches that are developed for mimicking pattern way of processing the information. Okay. But if you see computers or computing machines based on the Van Neumann architecture, they are basically meant for processing data. Now we have to enable the capability of mimicking pattern way of processing. That is, pattern recognition approaches are to be deployed on a computing machine. Just like we have machine level language, assembly level language, and high level language, even though computers still work at stored program concept and data, but we have to, one more layer will come where essentially we implement pattern way of processing algorithms, which even though computer at the basic level, they process data and also go by programs, but indirectly, we implement this pattern processing approaches, which are described under pattern recognition field. Of course, as after several decades of working in the pattern recognition, people evolved a new direction for the work, what is called machine learning. The genesis for this machine learning was in terms of with earlier, when pattern recognition field was there, people were talking about only a limited amount of data. They have to handle it very carefully to extract relevant features and then model it in a very constrained way so that we, with that limited resource, exploit to a maximum extent. Whereas with connectivity available and large amount of digital data easily accessible, people felt that that constrained way of handcrafting the features and dictating the machine how exactly it has to extract out the pattern from the features and model the pattern information, that is not a scalable solution if I want to deal with this large amount of digital data available at disposal. That is where they felt, is it possible to develop approaches which can automatically learn the pattern information from the large digital data without being explicitly programmed in the sense, strictly guided approach for the algorithm to do how to model the pattern itself. That flexibility is given to the computing algorithms to learn the pattern information or discover the pattern information that is present in the input digital data. And since there is a flexibility for learning the patterns from the input data, just as an excitement, they gave the word what is called machine learning. And in the machine learning, essentially we have learning algorithms which can implicitly discover the patterns that may be present in the input data. Input data is inherently a set of features. It is not raw data in the set of features, but we don't have to bother about what those features. This machine learning algorithms assumes that you have extracted the features and given features to that machine learning algorithm. It will in turn exploit the. Now, when the next field evolved, what is called deep learning, there even the feature extraction was given flexibility. Earlier in the machine learning, the feature extraction was still handcrafted features. So now with the deep learning, even features are derived implicitly by the deep learning models. You directly give the raw data into the deep learning models. First, they will extract the relevant features from the raw data, then use those features extracted implicitly for further discovering the patterns represented by the feature. So, hence the name deep learning came into picture, because both feature representations as well as the pattern representations are derived implicitly by the learning algorithms in case of deep learning. Just to summarize, artificial intelligence is that big field which contains all the approaches that enable computers to perform the intelligent task. One subfield in that is the pattern recognition. In this pattern recognition, both feature extraction as well as pattern discovery and modeling, both were handcrafted. Means there is no flexibility for a computing machine to discover any new way of extracting the features or the patterns. Whereas when you come to the machine learning, features are still handcrafted, whereas the pattern discovery was given flexibility, and that is where it is termed as machine learning. Then when further improvement came, when it goes to the deep learning, even feature extraction was also given flexibility. That means say the model itself, from the raw data, first it extracts the relevant features in the first few layers. Then it uses those relevant features for discovering the patterns. So this is the relations among all these four terminologies that are being exploited in the field. Now, going slightly more deeper into that, I told intelligent task. Intelligence, if you look at the dictionary meaning, it is the experience or ability to learn and understand and use it for deciding future course. When you look at the meaning of the word intelligence, it is nothing but experiencing and use it for deciding future course of action. This you can match with any activity that you do in daily life to survive as humans. We have any task you take, we experience first. Means first we try to learn and understand, and that develops some models in our cognitive system which will be used for deciding future course of action. So, for example, even learning the how to speak in a specific language, we through our auditory perception system we get exposed to several recitations of those sounds and words in that particular language from our neighborhood, parents, teachers, friends, and the neighborhood. So, as a result of that, it over time our cognitive system will discover the features and models, and those models are being used for in future course of action. When somebody speaks that particular word, the cognitive system matches with your stored patterns and say, okay, this is the word that is being spoken, and accordingly you will understand the message that is being called. So when you consider this word intelligence, it just means our basic ability of human species for survival, which is essentially experiencing, that is learning and understanding, ability to learn and understand and use it for deciding future course of action. But of course, nowadays people use this intelligence as a misnomer. That is, when you take this human intelligence, we will say it is attributed to the performance in a specific task, or more specifically academic performance. If somebody does very well, you say is a very intelligent guy, but that is nothing to do like that. Okay, it is this common basic ability of humans in terms of experiencing and use it to deciding future course of action is intelligence, and that ability provides you the capability for humans to sense information from their sensory mechanisms and act depending on the need. For speech processing is no exception. Suppose if I know a particular spoken language, somebody speaks in that spoken language, I am able to understand the spoken message. Then if I want to respond, I can respond in the same language, whatever the reply I want to give. And this is one intelligent activity by humans. The ability to understand the spoken message and the ability to reply back in the in the spoken forum is one intelligent activity by the humans. Then when we say if the machines should have the ability to recognize speech and produce speech, we should enable machines to perform this intelligent activity. Of course, when we take this intelligent activity by humans, it is attributed mainly to the cognitive system, or in a layman term we call brain, where we all experience how it happens, but it cannot be formally described because it is not decoded to such a detail. We all experience, we agree that we can, when I am proficient in a particular spoken language, I can understand the message produced in that language, and also I can produce message in that language. But how exactly my cognitive system does, that the human brain does, it is not decoded. Of course, production part, perception part in the ears, how the acoustic signal gets into our ear, goes from outer ear to middle ear, into converting what form the energy gets converted in the middle ear, from their middle ear, how it gets converted into bioacoustical potential in the inner ear. All those things are known. From the bioacoustical potential, how the pattern discovery happens, That is not still clear. But that we all appreciate this ability to learn and understand as well as use it for future course of action, that we treat it as an intelligent activity, then can I mimic that intelligent activity on a computing machine? And that is where this birth of the field artificial intelligence came into picture, enabling machines to do so-called intelligent tasks. Intelligent task means discovery, learning, dealing with uncertainties and new situations. Only mimicking. It is not, since we are not understood how it happens, we only mimic that activity in our own way, depending on what tools and techniques we have discovered at that point of time. Use them, put them in some forum, so that we will be able to mimic one of these activities, one or more of these activities, like discovering features, learning patterns. Then, when during testing, if some unknown situation comes, how to ensure that the performance of the system shows a graceful degradation. So all these things are the mimicking ability of the intelligent task. Of course, when you come to the artificial intelligence categories, there are two broad directions there. One is what is called symbolic manipulation, is one form of artificial intelligence. Then connectionist approach is another form of artificial intelligence. This neural networks and deep learning comes in this connectionist approach for as form of artificial intelligence. Of course, as I mentioned earlier, the field of artificial intelligence was there long back, few decades back itself. At that time also, it created the same hype as it has created now. However, that hype died down quickly without coming up with a good practical solution for any of the tasks that were projected. Even though people claimed that it can do great things, but maybe time was not ripe at that point of time to do the demonstrate the required robust system. If you see now that earlier attempt of artificial intelligence, just for better distinction among the two sides, because last one decade also people are talking about artificial intelligence again. That I view it as artificial intelligence 1.0, and now what is last one decade we are telling using connectionist approach as 2.0. If you take 1.0, the artificial intelligence solved the problems that are intellectually difficult for humans, but relatively straightforward for computers. Intellectually challenging, like people came up with chess playing software, traveling salesman problem to give an optimal path from source to destination. All these things, it requires large amount of thinking, and you need any amount of time you think is insufficient, and also always the output that you are deciding is always has a degree of uncertainty. It is a very intellectually challenging task. For example, chess game itself. Many of your chess players, you will appreciate that part. So there are so many moves possible. Out of that, which move I should take? Because I have to put myself in the shoes of the opponent. If I take this move, how he or she will react for my move. So based on that, all possibilities, things I have to think and then take a move. But still, I am not 100% sure what will happen. Only after I move, then the opponent move takes, then we say, oh my God, this I would not have done. Okay. But for a computer, with the computing abilities, it can parallelly think about so many moves possible. And from the earlier experience of playing the games with the opponent, it has stored all the winning moves. So based on that, it will pick out the best move among all the possibilities available. Suppose a human opponent can think only 100 paths because of that limited time. Computers can parallelly think 1,000, 10,000 moves and then give me the optimal move. So that is how in that artificial intelligence 1.0, they were finally able to develop space chess software which can beat human professionals of playing. Of course, even though that success was there, that success of coming with a chess playing game against the humans, and even he can beat the best proficient players in chess, but it did not, that solution or approach did not scale up for solving tasks which are very easy for people to perform. One of the example is speech recognition itself, but it is hard for people to describe formally. For example, we know if I am proficient in a spoken language, I can understand the message without any effort. I can produce the speech without any effort. But if you want to describe formally how your cognitive system is doing step by step, that becomes a hard task because an ill-posed problem. It is not formally described. We cannot describe all sort of nuances that happens in this speech activity. It is very difficult to. So unless you don't describe formally, it becomes difficult for the computing machines to mimic. So, for example, speech recognition, face recognition, fingerprint recognition, natural language processing, these are all very easy for humans to do. But if you want to mimic on a computing machine, that became very difficult for computing machines because we were unable to formally define carefully. Even the concept of expert systems came as a part of this earlier AI 1.0, where people bring subject experts in that area and he or she will formally describe all sequence of steps so that we can code them in the form of a programs, which we call it as expert system. But even then, even the subject expert will not be able to describe all possible steps that how they employ dealing with the natural data like speech. That is where the success of AI 1.0 limited only to those tasks which are intellectually difficult for humans but relatively straightforward for computers to deal with, because intellectually difficult but we can formally describe all parts of moves given enough time. Such things AI 1.0 give a very good solution, but which are easy for humans to perform but we cannot describe them formally. For such a task, AI 1.0 it was not successful. Last one decade, with the success of connectionist approach for artificial intelligence, which seemed to be with that successful performance in the system, looks like it has provided solutions that seemed very difficult or hard in AI 1.0, which are intuitively easier for humans to do but difficult to describe formally. For example, speech recognition seems to be providing very good performance nowadays. Even computer vision tasks, you might have seen, they are performing very well, even comparable and even surpassing, in some situations, surpassing the human performance, computer vision tasks. So, that is what caught the attention of the community, both academic and commercial community or industrial community, of seeing that yes, this version of artificial intelligence seemed to be giving some solutions which can indeed be used in the practical scenario. So that is true for speech recognition. That made very good performance in the speech recognition and other speech technologies, which made them to deploy solutions in the public domain. And people seem to be using them on a regular basis. That to the next generation, which are tech savvy, they nowadays, instead of typing on a very small keyboard available on a smartphone, they just speak into the smartphone. And interestingly, the performance seemed to be very good, which is tolerable from a human acceptability rate. Tolerable means, suppose I don't mind when I speak 100 words, if one or two words gets wrong. However, most of the words I don't have to type these 100 words using that small keyboard. Okay, so it is there in that acceptable. That is how you see a lot of speech applications or technologies coming into the field. Coming to the approach that was taken, pattern way of processing you were taken from the pattern recognition to the deep learning, from the handcrafted features people used to use and a strict regiment of how to discover the pattern. In AI 1.0, we have reached to a stage where we can feed raw data into the deep learning models. It will first discover the relevant features, non-linearly processed relevant features, then further process those non-linear features to discover the patterns which are there in the data. Okay, so that is the gist of how this whole field of we have reached from deep learning to machine learning to pattern recognition, machine learning, and deep learning. Now, specifically coming to the motivation of deep learning, the way the deep learning models extract relevant features from the raw data first, and then process this raw data through the several layers of processing to discover the patterns, may be matched or better understood by comparing the human way of learning. If you take the human way of learning, it is learning from the experience. That is what we do. Anything we do, we become proficient over time on a particular thing when we learn from experience. Of course, one of the best, of course, many examples can be said. For example, if you have learned driving a car, you can imagine on the first day of trying to learn the driving, and now your proficient level of confidently driving your car across the street roads and reaching your office. You yourself can appreciate how was your proficiency on the first day when you went for a driving school, or through your friend you tried to learn. You are very scary even to touch the steering, switch on the key, and because you don't know what to do. But based on the but it is not that first day you just sat in the car, started the ignition key and started driving rashly on a public road. Okay, so when that driving way of learning the driving, if you take, you don't have to learn all the nuances on the first day itself. First day you learn some basic etiquettes of when you want to learn driving. Then you practice that for a few times. Then you add one round of complexity to that. Then you handle one more round of complexity to that. Then go on increasing the complexity until you become very comfortable to handle the most difficult scenario of driving in Indian roads. But even that, it does not mean that you have learned all possible situations, because every time of driving on an Indian road is an experience, because so many uncertainties come on when you are driving. You don't know from which directions which vehicle will come, who will overtake, whether he will overtake from the left side, right side, or even you can drive over your vehicle. That is how Indian roads we drive. But in spite of that, we are able to confidently move through. And that is where first you learn in a very simplified manner, then go on adding complexity. With more and more complexity, you will become more and more proficient to do that. Same way it happens in deep learning also. You need not specify everything in the beginning on what patterns to discover, how the pattern should look, what feature to extract, how many number of features to be extracted. All those things you don't have to worry. You treat this process of learning, of becoming a proficient driver from a first day where you don't know how to drive. You describe, sorry, just one minute. So if you describe this, the whole process of learning, you can describe it as a hierarchy of concepts. So for our hierarchy of concepts, there are something called low-level concept. Then use first from the raw data, you learn this low-level concept. Then using this learned low-level concept, you go to the next level of concepts, which can be better learned using this low-level learned concepts. Of course, you can also use the raw data if you want in addition. But once you learn that next level concept, using those next level concept, you go to the next higher level concept and finally reach at the pattern discovery, what you want to have. And that is that hierarchy of concepts. So each concept is defined in terms of its relation to the simpler concept. So learning complicated concepts out of the simpler ones is the human way of learning. And we can view this deep learning framework, which essentially if you take any deep learning network, which has people say about having several hidden layers and each layer having several nonlinear elements with so many things available, what is that is being learned when we are feeding raw data? At least we can appreciate it better by viewing this human way of learning, where you learn as a hierarchy of concept from the raw data. First you describe some low level of information, then that low level of information you combine them to get next level of concept, like that until you reach the final this one. Okay, so that is the thing people have taken as a motivation for deep learning. That is how we directly feed the raw data into the deep learning networks and try to allow the network to learn the features first, and then use those features as a low level concept, then use those features to learn the high level concept or pattern discovery. Now, coming to the feature pattern recognition, as I mentioned earlier, it is a task of feature extraction, modeling, and recognizing the patterns. Just excuse me. So, Ashraf, am I audible?
Yes, yes, sir, you are audible. No problem.
Thank you. Just 1 minute.
Yes, sir, yes.
Sorry for that interruption. So far I described about up to the motivation for deep learning from the human way of learning. Coming to the pattern recognition, if I want to slightly mention the differences among them, let me see whether I can project the new screen. Okay, so okay, so is this white screen visible?
Yes, yes, sir, it is visible.
Okay. Let me see. Pattern recognition block diagram. If I take, suppose if I limit this pattern recognition block diagram to speech processing, this is the mic into which you are giving the acoustic signal, speech. So here, the first block in that pattern recognition will be feature extraction. Then from the extracted features, you do the modeling, then use those models and then the extracted features for comparison. Then you get recognized patterns. Suppose if we see this whole thing of feature extraction and modeling, this we call it as training or enrollment. Alternatively, if I take the same feature extraction and comparison, because during testing there is no training, okay, and this is called as testing stage. Now, if I consider this pattern recognition system, it will have an important module called feature extraction block, then a module called modeling. So this feature extraction is from the incoming raw speech signal, you extract relevant features. For example, in case of speech, we have this workhorse called mel frequency capital coefficient. The signal processing algorithm processes in this feature extraction block to extract the relevant features, that is MFCC features. Now, these MFCC features is applied to the modeling block, which contains any of the pattern discovery models. Like earlier, before deep learning came into picture, we had Gaussian mixture models, hidden Markov models, neural network models, support vector machines. So that discovery and building the models for each of the class or phonemes or sounds in a given language takes place in the modeling. This whole red block diagram, including feature extraction and modeling, will constitute training or enrollment. Then during testing, unknown pattern information comes. There I want to find out what is the pattern information present in the data. There I don't have to do the modeling. I extract the same features because then only we can compare. That's why the same feature extraction module becomes common. And then you compare that with the trained model in the comparison block. Essentially, the trained model and the extracted features are compared by an algorithm to see to which trained pattern these features mostly belong to. Based on that, you recognize the pattern. For example, if you take a digit recognition for 1, where you have spoken digit 0, separate model, and so on. For 9, I have built a separate model. During testing, the speech data can come from any of those 10 digits. Those MFCC features are extracted, and those are compared with all the 10 models to whichever model it best matches in terms of likelihood, probability, or something. I will describe them as the recognized pattern. Okay, so this was the thing which was there in the case of a pattern recognition system. Suppose if I go for pattern recognition literature, what to do, what feature to extract, MFCC feature to be extracted, there is no flexibility for a computing machine to look for any new feature coming. It's only blindly processes to extract the MFCC features. When I go for modeling, suppose if I am building Gaussian mixture models, no flexibility. Use the just Gaussian mixture model algorithm to blindly take the MFCC features and build the model. So that is where we used to call, if I go for, let me see whether I can take a new color. Let me show. For example, if I go for pattern recognition, PR means pattern recognition, handcrafted, both feature extraction as well as model, both are handcrafted. No flexibility for the computing machine. It blindly crunches the number to get this one. The same block diagram will be there when I go for machine learning, where handcrafted features, however, model or pattern discovery, flexibility is there. Pattern discovery flexibility is there. On the other hand, when I go for deep learning, flexibility for both feature extraction as well as modeling. Okay, that is the difference among the three fields: pattern recognition, machine learning, and deep learning. Where here in pattern recognition, everything is pre-decided by the algorithm. What feature to extract, how to model the pattern information from the features is all tied tightly by the algorithm. When I come to the machine learning, features are still handcrafted features, whereas the model pattern discovery still has flexibility. Means you can discover your own way of patterns present in the exhibited by the features. Then after that, when I come for the deep learning, even feature extraction also given flexibility in the deep learning network. So that is what I wanted to say. Let me go back to these slides. Slides are visible now?
Yes, it is visible.
Yeah. So now, if I go for pattern recognition, feature extraction, modeling, and recognizing fashions that are not directly observed from the raw data, which is essentially deals with mimicking human way of dealing with natural data. Sensing, sensing is done by microphone, feature selection by MFCC, model creation by any of those models like JMM or HMM, and then comparison block. Ability to demonstrate pattern recognition approach of the humans was done. Of course, we heavily borrowed from the knowledge that is available in signal processing, statistics, and stochastic or probabilistic modeling. Of course, at that time, we had limited computing power, limited amount of digital data to deal with. We just conceptually mimicked the human way of dealing with the natural data. Now, coming to the machine learning, I was harping on too many times about there is flexibility for modeling. With more and more digital data available, task of automatic discovery and learning of patterns, both natural and synthetic data, became a need because it is not possible, humanly impossible for not directly amenable to your particular algorithm. That is where the more emphasis was placed on discovery and learning of patterns by the machine. So this learning can be simplified way. Machine learning can be in a simple way. We can indicate like this: given set of features X and the corresponding pattern information is Y, this Y is equal to f of X, where f represents the functional relation between X and Y. And the goal of the machine learning is to learn this functional relation that exists between the input and the output data. So with that simplified view, I don't have to specify what is this nature of this function. I can take the raw data available or the raw features available. Based on the distribution of the features, I can learn the feature mapping that exists between the input and output. So the whole simplified way of using machine learning is essentially to learn the functional relationship that exists between the input and output. With that type of simplified view for pattern discovery, then we can quickly scale up this pattern recognition to the wider problems. For example, when I look into the speech domain itself, there's a lot of domain knowledge required. Somebody to first what feature to extract, how to model. He should be an expert in the speech processing area or signal processing area. But with this machine learning came, with the simplified view of functional mapping, the people have got flexibility in terms of they don't care how these features were extracted. Just given the features, they took it as designing a learning algorithm which essentially discovers the functional map that exists between the input and output data. So with that, not only electrical signal processing community started working in machine learning, computer science community and many other community without domain knowledge also can start using working in the machine learning field. That is how the widespread community of machine learning came into the field. Further, what happened is you don't have to worry too much into working in a new area because you don't require a domain knowledge. For example, this machine learning algorithm can be used for discovering the patterns in case of speech. The same algorithm you can go and apply to analyze the stock market data, or even to find out the market trends, sales statistics, sale trends of supply chain management or what we call chain of shopping malls across the country. People can, because the same shopping mall is there across all the, starting from Silchar to Guwahati to Bangalore to Chennai, same shopping Reliance or something are there. So how they want to discover automatically what is that, which products are being sold in that particular region. That gives us a knowledge on stocking and transporting the material that can be done by machine learning. So that is how the widespread use of machine learning came into picture. Then, but in the machine learning, as I mentioned earlier, we had this flexibility in terms of features extracted by some algorithm. We don't care, but only worried about the finding the functional relation between those input features and the model. Whereas the deep learning, even that flexibility was given. Even learning the features, that is the representation, and also patterns, both are done automatically by the machine without much specific description by the humans when they are using for the task. Only you give the raw data, give the task goal, apply to a deep learning model. We are hoping that it learns as a hierarchy of concepts. Okay. Now, of course, if I come to the neural networks, if you consider deep learning, it is the previous avatar of deep learning was nothing but neural networks, because both, if you consider neural networks and deep learning network, both have layered elements, and each layer has a set of nonlinear elements for processing the data. Then what is the difference between neural networks and deep learning? Okay, so here, one structurally, if you see, there are more number of layers in the deep learning network. Also, in each layer, the number of nonlinear elements will much higher than what is there in the conventional neural network. So, but of course, people blindly say, "Oh, deep learning network is a huge neural network model, and that is why the deep learning terminology has come." Even though the structure is used, the deep learning terminology is more attributed to the information that is learned from the raw data. First, it can learn the representation, which is nothing but features, then use those learned features for further discovery of the patterns or modeling purpose. So that is why it is learning in a better manner compared to the conventional machine learning approach. That is how one of the main reasons for calling it as a deep learning model. Okay, so even if you take deep learning, also we have feed-forward neural network architecture, which is a deep learning model. Also, will have a feed-forward architecture, which is extensively used. And if you take backpropagation learning algorithm, that is one of the workhorse algorithm for learning the parameters of the feed-forward neural network. Only thing is, this backpropagation learning algorithm did not work well for networks that have more than a small number of hidden layers. Even if you refer back to the literature of neural networks, if typically one hidden layer, or some of people have explored 1 to 3 hidden layers. Beyond the 3 hidden layers, the performance starts getting saturated, or you don't really get a very improved performance by adding more and more layers into the network. That's what is meant by this backpropagation algorithm did not work well when the number of layers are more than few layers, maybe beyond 3 layers or something. Okay. That one of the reasons that can be attributed is the occurrence of the local optima or minima in the non-convex objective function of the deep networks. That is, the networks which have more number of hidden layers is the main source of difficulty for learning when we were using only backpropagation learning. Now, when it comes to the breakthroughs in the deep learning, this can be attributed to the paper published by Jeffrey Enton group, who is treated as one of the founding fathers of the deep learning network. They demonstrated a deep belief network could be efficiently trained using a greedy layer-wise pre-training. That was demonstrated in 2006. That means to say, when you have multiple layers, since the backpropagation learning algorithm is unable to properly train the network, you take each layer separately and train each layer separately. Layer-wise pre-training you do, then you stack all those layers, then you use your deep backpropagation algorithm only just to adjust some final fine-tuning of those weights which you have learned by layer-wise training. They found that with that, you are able to achieve much higher performance compared to what you are unable to achieve using the conventional neural network using backpropagation learning. Of course, when this group published that work in 2006, other research groups who were fascinated about the deep learning, they also took for other forms of deep learning network the same strategy. That is, layer-wise pre-training was exploited, and they trained the deep networks and demonstrated that yes, it is indeed, that's a good way to go about. That is layer-wise pre-training and then stacking them together and fine-tuning is a good way to go about for deep learning networks. And this made to train deep neural networks, which has not been possible before. Okay, and then it was shown that these deep neural networks outperformed the AI systems which are earlier developed by other machine learning technologies and hand designed functionality. For example, if you consider earlier versions of machine learning techniques like even neural networks itself, having one or 1 to 3 layers of hidden layers or support vector machines, hidden Markov models, which are maybe treated under machine learning technologies. Compared to them, the performance by the deep neural networks was much superior, and which was consistently demonstrated across several groups. That is where it caught the attention of the whole community. So these learning algorithms reaching human performance on complex tasks, nearly, if you look at the, for example, layer-wise, greedy layer-wise pre-training, if you see, that is not any magic thing which came out suddenly out of the blue. It was a iterative approach. People struggled for decades. This algorithm, if you see the training process, it is identical to your earlier learning algorithms. People struggled to solve the toy problems in 1980s. However, uh, the the models that we have training nowadays under the caption a badge of deep learning have gone through a radical change of having many number of hidden layers and also a large number of neurons in each, and the availability of a huge amount of digital data to train such a big network made them to show a successful performance which is much higher compared to the conventional ML algorithms that were there. Okay, thus just to take an example of acoustic modeling, for example, if I take speech, you can use it for speech. People use it in communication area or versus speech processing. If you go for a communication, electrical communication area, we mainly treat from the compression point of view, how efficiently I can code the speech signal. But we are not extracting any relevant information, extract and model relevant information, which is not the goal of electrical communication, but the goal of speech processing. Information means I may be interested in doing speech recognition where I am interested in message part. I'm interested in identifying the language there, the language information I have to extract. I'm interested in speaker recognition, then I'm interested in the speaker part. If I want to do gender information, we have gender, this one, emotions, health condition, many things. These are all the informations where the deep learning approaches will help us to extract relevant features and model this information for doing any task on a computing machine. So, as I mentioned earlier, if you take the speech processing and compare human versus computing machines, the human cognitive system is good at modeling information present in the speech. We experience that, but it is difficult to describe formally. So, computing machines is trying to mimic some of these activities for decades, which may be viewed under pattern recognition machine learning approaches. Then the last 1 decade attempts, starting from 2012 landmark paper on acoustic modeling by Hinton and other groups, the computing machine, there are many new approaches came, which are all can be grouped under speech processing using deep learning. They seem to be giving very good performance. Suppose if you see broadly some of the approaches that are coming under the pattern recognition machine learning for speech processing, these included clustering, dynamic time warping, Gaussian mixture models, hidden Markov models, neural networks, support vector machines. All these things can be viewed as pattern recognition machine learning approaches for speech processing. Alternatively, if you come last 1 decade and referring to the literature, we have started with deep feed forward neural network, which included one of the architectures, deep belief networks, then deep autoencoders, generative adversarial network, convolutional neural network, time delay neural network, many more came as deep architectures, which have been exploited in many speech processing tasks. Of course, all these deep learning frameworks, architectures can be viewed in three broad categories. Either they are unsupervised or generative learning, or supervised learning, or a hybrid of these. Any of these deep architectures if you take. Depending on the task under consideration, you can use one or more of these architectures too. Now, as a one case, as I told, this paper by Professor Jeffrey Hinton and many other groups from University of Toronto, that is Professor Jeffrey Hinton, then many from IBM, Google, and Microsoft, all four groups worked together and published this paper, Deep Neural Networks for Acoustic Modeling in Speech Recognition, the shared views of four research groups, which came in Signal Processing magazine in August 2012. The material is taken from there. Now the approach of this one is, this acoustic modeling is the one of the basic important kernel of automatic speech recognition. People demonstrated how a deep neural network can indeed show a significant improvement in performance compared to the earlier version of the acoustic model using Gaussian mixture models and hidden Markov model combination. Who are working in the speech processing will appreciate this point. This combination of Gaussian mixture model and hidden Markov model was there as a very strong modeling approach for several decades for acoustic modeling. There was no challenge. Even the earlier artificial networks came as a challenge, alternative direction for this GMM HMM approach for acoustic modeling, but they were not successful to outperform the Gaussian mixture model. Okay, but what people have found that was their Gaussian mixture models are good when the distribution of the data follows a Gaussian distribution, whereas if you go for a nonlinear manifold, if the data is in a nonlinear manifold, at that point, even you need a very large number of mixture components to model that, because any nonlinearity to approximating the nonlinearity requires large number of components, which computationally very expensive. So that is where they were not very efficient in modeling the distribution of the data which are there in the nonlinear manifold. That is where the beauty of this deep neural network comes. They can handle this nonlinear manifolds by the deep neural network architectures. Now, if you just quickly see the artificial networks for acoustic modeling earlier, artificial networks trained using backpropagation learning, which is the workhorse algorithm, had the potential to learn better models of data that lie in the nonlinear manifold. That was one of the motivation for using artificial neural network, that they indeed learn the data in a present in the nonlinear manifold. And suppose one of the landmark works earlier, if you see Arlard and Harvey Ballard and Nelson Morgan, they have a paper, Connectionist Speech Recognition book, hybrid approach by 1993. They demonstrated that with a single layer of nonlinear hidden units to predict the HMM state information. In GMM, HMM, GMMs predict the HMM states, but here they use neural networks. However, what happened was they were unable to take it beyond one layer, mainly because at that time, neither the hardware, neither the hardware nor adequate training data was available for training the neural networks with large amount of data. So, therefore, even though neural networks came as a challenge to the GMM HMM combination, but their benefits of using neural networks was only limited to a single hidden layer. So accordingly, not sufficiently large to seriously challenge the Gaussian mixture model. That's where they settled to a situation where the main practical contribution of neural networks at that time was to provide extra features in addition or a bottleneck features along with this conventional MFCC to better train the acoustic models. They were not the alternatives to seriously challenge this one. Whereas this 2006 work by Jeffrey Hinton's group on layer-wise greedy training, that gave the breakthrough for using deep learning networks, where they follow a two-stage training procedure for training the deep neural networks. In the first stage, each hidden layer is trained separately, okay, by fitting a stack of generative models. Each of has, for example, one layer of the hidden layer is taken and trained separately in the first stage. So, for example, if I take the first hidden layer, the input is the raw data, and the output is whatever the latent variables or hidden information that they want to learn as the output. Then once I train the first hidden layer, when I want to train the second hidden layer, pass the raw data through the trained first hidden layer. The output of the first hidden layer, whatever we get, that latent variables or hidden variables, they will be acting as input to the second hidden layer, and the second hidden layer again trained. Like that, layer-wise pre-training is done. Then, in the second stage, what it is done is each generative model. That is where the each hidden layer can be treated as a separate generative model, and each of these generative model, they are used stacked together in the as hidden layers in the deep neural network. Essentially, use the parameters, weights derived from the layer-wise training in the deep neural network, so that I don't start from a random initialization of the deep neural network. I use well pre-trained weights as the weight for the deep neural networks, and the whole network now, since the weights are properly trained, is discriminatively fine-tuned using again backpropagation algorithm to derive the HMM state information. So that is where this came as a different strategy for training the deep neural network, layer-wise training, and so that is where, if same information I have told, issues in training the deep neural network is deep neural network with many hidden layers are hard to optimize by using conventional backpropagation algorithm. Mainly because if you go for backpropagation algorithm, the gradients or the slope that we derive, error slopes that we derive, want to backpropagate, will have very different magnitudes. Starting from the output layer, if you just come inside a few hidden layers, you end up in a well-known problem called vanishing or exploding gradient in different layers. So, very large amount of training set can reduce this overfitting to preserving the modeling power, but only making training very computationally expensive. So that is where this layer-wise training, better method for using this information in the training set to build multiple layers of nonlinear feature extractors. That is where layer-wide pre-training helped. That is where generative pre-training of the deep neural networks came into picture, where instead of designing feature detectors to be good detectors for discriminating between classes, design them at modeling the structure in the input data. That means to say, when I'm training layer-wise first hidden layer, feed the raw data into it and try to extract some higher level information, whatever it gives from the raw data. And there is no description for that. Only I will say, okay, I will project this raw data of 1,000 samples to some 50 dimension output. That 50 dimension non-linearly extracted features, we view that is learned some whatever the input information was there in the time and 1,000 dimension, now it is represented in 50 dimensions. So that is a learn one layer of feature detectors at a time with states of feature detectors in one layer acting as data for training the next layer. So after generative pre-training, multiple layers of feature detectors can be used as a much better starting point for discriminative fine-tuning, during which backpropagation through the DNN slightly adjusts the weights found in the pre-training. So the generative pre-training finds a region of the weight space that allows discriminative fine-tuning to make rapid progress. and it also significantly reduces the overfitting. That is where the advantage came. Just to give a performance on the well-known timid database, earlier the Gaussian mixture model HMM combination gave a phoneme error rate of 27.3%, whereas the initial version of DNN using randomly initialized weights gave about 23.4 performance. Monophone deep belief network layer-wide training of deep network gives about 22.4. On the other hand, instead of deep belief network, people tried with convolutional neural network, which with on filter bank energies, which gave 20%. So you can see for about nearly 3 decades, people were hovering around 27.3%, maybe 26.1 or something. It will be hovering around that only. Suddenly, they showed about nearly 7% improvement in the absolute improvement in the performance, which people struggled for 3 decades to achieve. This can be attributed to the deep neural network architectures, which essentially can be given to the deep learning architectures as well as the layer-wise pre-training that was employed. That phoneme recognition performance can be evaluated on a speech recognition in terms of word error rate, where GMM HMM based speech recognition system was built. We gave a word error rate of 23.3% on one database called Hub database, 27.4 on RT03S database, whereas the DNN gave about 16.1. From 23 it came to 16.1, from 27 it came to 18.5. That shows nearly about 7 to 8% improvement in the performance, which was a very difficult thing to achieve. This fueled a lot of activity in the speech recognition, and there is no turning back. The rest is history on coming up with very good deep architectures. I just ever demonstrated for speech recognition. Many other tasks it has been done. Just to summarize, there is a significant progress in adding values to the computing machines and making them to handle this intelligent task. Starting from pattern recognition, the latest trend is this deep learning. Signal processing, statistics, stochastic modeling, pattern recognition, machine learning, and deep learning. That is the flow of evolution of the technology in the connectionist approach for AI, artificial intelligence we can take. This deep learning resulted in several speech technologies that gave widespread practical deployment. Thus, the latest trend in deep learning seem to be providing significant improvement in the performance. So that is why there is no looking back in terms of replacing the deep learning model, going back to the machine learning model. So that is what I wanted to say. I think with that, I will stop my presentation here. If there are any questions, I will be very happy to take. Thank you very much for your patient listening.
Thank you, sir, for your nice presentation.
Thank you.
I think, sir, please go through the chat box where one question is there.
What is the challenges of pattern recognition? That I explained in the talk, that if I go for pattern recognition field itself, in the conventional way, what we are studying as a course, the feature extraction module, training module, all of them are handcrafted. Means a priori decided. For example, if I take MFCC feature extraction algorithm for the speech case, it blindly crunches the raw digital speech samples to extract MFCC features. Even the raw speech data has some additional information which can be better useful for doing a speech task, but there is no way I can extract that because I'm using this handcrafted MFCC feature extraction algorithm. So, in nutshell, if I want to say, all the modules in the pattern recognition system, they're all handcrafted or tied strictly based on the algorithmic steps, what to discover. There is no discovery there, it just crunches and gives me the numbers. Whereas when I come for the machine learning, that is where they've observed this limitation of the pattern recognition, and then that is how the next evolutions have come in terms of machine learning as well as deep learning, where flexibility is given to both feature extraction and modeling. Hope I have answered that question.
Okay, sir, thank you. I think there is no other questions. So it is the time to give the vote of thanks to the speaker. So thank you, sir, for enlightening the talk on speech processing using machine learning. I hope that participants have been benefited by your valuable talk. Thank you, sir, for being with us and delivering your nice presentation, and hope your association with NIT Silchar, especially in the Department of Electronics and Communication Engineering, will be continuing in near future also. Thank you, sir, for your valuable time.
Thank you.
Thank you very much.
Thank you, Ashraf, and thank you all for patiently listening for nearly 1 hour 20 minutes.
Yes,
Thank
sir.
you, Rabul, for this opportunity. It will be my pleasure to get associated with NIT Silchar. Thank you very much.
Thank you, sir. Very much.
Thank you. Thank you very much. Thank you all.
Sir, you
Thank
can.
you. Thank you.
Thank you. Thank you.
So, dear participants, so first session of the third day is over. Now the second session will start around 11:35. So 10 minutes times are there. So next speaker is Professor Pritam Kumar from IIT Patna. He will talk about 5G and its challenges. Thank you very much. Good morning, sir. Welcome.
Very
Professor
good
Pritam
morning.
Kumar.
Very good morning.
Good morning, sir.
How are you?
Sir, fine, sir. Hope you are also well.
Yes,
Sir,
yes.
So, shall I start, sir? The
Yes,
procedure?
yes, sure. Please
Good
go
morning
ahead.
to all. Good morning to all. Welcome to the second session of third day of 5 days webinar on recent trends in signal processing and communication, RTSPC-20. I am Ashraf Hossain. Welcome you, all the participants and our esteemed speaker, Professor Pritam Kumar from IIT Patna. So before starting his session, it is my pleasure to introduce Professor Pritam Kumar. So Dr. Pritam Kumar is currently working as an associate professor in Department of Electrical Engineering, IIT Patna. He did his PhD from IIT Kharagpur in the area of wireless cellular communications. He has around 20 years of teaching, research, and industry experience. Physical layer issues in wireless communications, 5G network, error control coding, and digital communication systems are his areas of research interest. He has published several research papers in various referred IEEE journals, other peer-reviewed journals, and conferences. He is a regular reviewer of premier journals and TPC member of various conferences. He was the organizing chair of first IEEE symposium on 5G in Asia at IIT Patna. He has supervised 7 doctoral theses and more than 30 MTech projects. He has also successfully executed a number of high-value sponsored projects from Government of India as well as consultancy projects from industry. Apart from his research and teaching activities, he is also part of many administrative and governing committees, member at IIT Patna and other premier institutions all over the country. He is also serving as the editor of Springer Wireless Networks and Wireless Personal Communications Journal. So with this brief introduction, it is our privilege to invite Professor Pritam Kumar. Sir, over to you. Now you can, so Professor Pritam Kumar will talk on the 5G challenges and enabling technologies. Sir, it is over to you. Thank you, sir, for your session.
Thank you, Ashraf. Thanks for the introduction. And good morning to all participants. And because it's a faculty development program, so most of you are faculties, maybe some students will be there, right? Ashraf, the students are also there?
Yes, sir. The students and the faculty members are there. So different spectrum of the audience are there.
Very great, great. So it is really a privilege for me. Yes.
Sir, this Google Meet is going to be broadcasted to YouTube channel, sir. So there, students are attending your talk, sir.
Yes.
Good, good, very good.
Sir, have you shared your PPT?
Just now I will share now.
Okay, sir.
Is it visible now? Asraf?
Yes, it is visible.
Okay, okay, great. So, welcome you all to this around 1.5 hour session on this 5G, that is challenges and key enabling technologies. So, all of we are in the era of 5G. Although in India 4G is being rolled out at different places. Services are available in cities and town, but still, because India is a vast country, we have to deploy 4G services at different places, remote villages, and we are looking forward that 4G will be fully functional throughout the country, maybe another 2 to 3 years. But in between, this 5G has already started to make lot of advancements, and for the last I think 5 to 7 years is the during this period the development in 5G is enormous. And so during this lecture, what we will try to figure out is that so what are the challenges, because we are already in a very advanced wireless communication era where we are using this 4G, which is a really good standard, which is good service. We are able to do all the required, whether we are in industry or academia or anywhere else, we are able to get all the services that is required in the present state of the art situation. But then why this 5G is coming, and then if 5G is coming, so what are the real challenges in 5G? And then if there are challenges, what are the technologies which are going to help us to help these challenges? So because I'm happy that there are BTech students also. So yeah, initially I will be talking about some fundamental concepts, because which is very fundamental. These concepts are very important for the development of 4G, and definitely that will be a part of 5G. So I will go through some fundamental concepts, and then gradually I will move on. So contents will be brief. I will give a brief introduction, then some detail about the 4G technology, then the requirement for 5Gs, challenges and facilitators. Which are the challenges and what are the facilitators? Dual track. How this 5G is going to be implemented. It has two tracks. One is evolution, and another is new radio access technology. And these are the RNA technology areas: new waveforms, millimeter wave, massive MIMO, HetNet, cognitive radio, D2D communication, and so these are the RNA technology areas which are very important to implement this 5G and find their conclusions, right, and references. So coming to this first slide, that is on evolution of wireless technology. Let us have just some idea how the wireless technology is evolving. And if you can see this graph, just give you maybe another 30 seconds to all of you try to observe this graph. What is given on x-axis, what is given on y-axis, and what are the services is mentioned, right? So that I'll be able to explain you properly. Just have a look on this plot.
Sir, sorry for interruption, sir. Sir, your slide is not coming. Only first slide is visible.
Oh.
You go to the, sir, please go to the slideshow mode, and then now it is coming. Second outline.
Okay. Now.
Now
is visible.
Graph is visible.
Okay. So what I will do, I will initially I will in slideshow, then I will go to the full screen, right? Okay. So this is now visible.
Yes, sir, yes, sir, it is visible.
Okay. So these are the outlines of my talk. This is LTE 4G. So first we'll go through the introduction, then we'll go through the 4G, because moving towards 5G, we should have a strong understanding of 4G. Then the requirements for 5G, challenges and facilitators. Then how this 5G we are going to implement. So it has two tracks. One is the evolution path, and another one is the new radio access technology that will totally new, which are not part of this 4G, and this will totally a paradigm shift from 4G. And these are the R&D technology areas which will be important for to implement this 5G, new waveforms, millimeter wave, massive MIMO, HETnet, heterogeneous networks, cognitive radio, D2D communication, right? These are the important R&D technology areas. So a lot of research is going on. So some of you may be interested to take it as your BTech project or MTech project or PhD work or maybe some research project. And then finally conclusion and references, right? So this is slide visible, Ashraf? Is this slide visible to all?
Yes, sir, it is visible. Just if you make it full screen, then it will be very good.
Okay.
If you make it a slideshow or full screen, then it will be good, very good.
Right. So, so just have a look at this diagram where we are talking about evolution of wireless technology. All of you just have to give some look at this, then I will explain it, what I mean by this, because a lot of information is there. So just have a close look and then I will explain it. So what this plot, it has a lot of information. So let us see one by one. So on the x-axis we have this data rate, and the y-axis we have this mobility and coverage. And mobility is defined by whether it is fixed services, it is pedestrian, or it is vehicular, indoor and outdoor. Based on that, we define this mobility. And the coverage is whether it is indoor coverage and outdoor coverage, right? And then we have a red curve, linear curve, that shows the spectral efficiency, right? So, then we have different services we have mentioned, that 1G, 2G, 2.5G. So where these services are, just positioned with respect to this data rate and mobility and coverage. So 1G, 2G, then 2.5G, 3G, then 3.5G, 3.75G, then 4G. So if you observe that, so one point is that when we are moving from 1G to 4G, so mobility is increasing, coverage is increasing, and data rate is increasing. That is one thing very clear, one important information from this. Second information is that about the switching part, circuit switching or packet switching. So maybe some of your BTech students, they are not aware of the circuit switching. So circuit switching is basically a dedicated end-to-end service where resources are available to the to users. Dedicated resources are available. So it is quite good for the quality of service, but it is very expensive. And the packet switching is the best effort service where we are not giving end-to-end resource, and total information is converted to packets, and they are routed through different paths from different channels, different nodes, and finally we are trying to ensure that the service is good. So if you observe that this initially this 1G, 2G, and 2.5G and 3G, part of 3G, they were circuit switch, and finally this when we move to 2.5G and 3G, so they have some services on circuit switch and mostly on packet switch. But when we move beyond 3G, it is totally a packet switch network. That is IP-based network. So 3.5G, 3.75G, 4G, and beyond that, maybe that's 5G, and all. They all are packet switch. This should be always kept in mind. Switching will be packet switching. That is, your services will be IP-based services, right? And there are some other services like WiMAX that does not come under some standard. That is 3G or 3.5G or 4G. They have different standard. that is 802.16 WiMAX. WiMAX is also very important services. And then we have this 4G and beyond heterogeneous network, that is 5G, that is coming at the right side of this graph. And then we have Wi-Fi 802.11 and Bluetooth 802.15. So some of them, they are working on the unlicensed band like Bluetooth and Wi-Fi. They are working on unlicensed band. So they are very popular because they are working on unlicensed band. So they are able to give you service with a very low investment, right? But most of the services are on the licensed spectrum. If you see the second half, it is the licensed spectrum. So what we have observed in the previous slide is that very important point. The evolution of wireless technology from 1G to 4G has witnessed improvement in different aspects like mobility, coverage, data rate, quality of service. So when we are going from 1G to 4G, it's very natural to think that there will be improvement in all these four important parameters, that is mobility, coverage, data rate, and quality of service. And this is important for the BTech students, that 1G and 2G was based totally on circuit switching, but 2.5 to 3G, they are both circuit switch and packet switched. But when we moved from 3.5G to 5G, that was packet switch, right? And this has a very important impact on the design of 4G and 5G wireless systems. So all the evolving generations are using licensed spectrum like 5G, 4G, they all are using licensed spectrum, but there are services like Wi-Fi, Bluetooth, and WiMAX are using unlicensed spectrum, so that they are easily available and we can do a lot of experimentation on that, and they are quite cheap. The cost is less, and so it is widely. So we all are using Wi-Fi. There are a lot of Wi-Fi services, free Wi-Fi services we are getting. So Wi-Fi service is free at so many places. So that is the reason, that because we are not paying for license to get that spectrum. Now, so this is somehow I'm trying to confine you, or I'm trying to highlight the importance of 2G wireless cellular standards, because everything has evolved from 2G. 2G is still very prevalent because a lot of services, voice services, are still on 2G. So, so 2G wireless standard, and this is legacy standard. So we have to just try to understand how from 2G we have evolved. That is the basic one, digital. So 2G is the first digital standard. So if you see this this table, we have of generation. We have 2G, then we have standard, which are the standards, and then data rate. So, so two important standards, that is GSM and IS-95. GSM and IS-95, that is IS-95 is totally based on CDMA, and they ensure a data rate of 10 kbps only. So now you can imagine that GSM, what we are using right now for speech communication, they have only data rate of 10 kbps. With IS-95, 10 kbps. Then what was need? That's what there was need to move from 2G because the data rate was very less. So we moved to 2.5G. So 2.5G has two standards, that's GPRS and Edge. So we all are very familiar with GPRS. So GPRS and Edge are basically a 2.5G standard, and GPRS are able to give you 50 kbps, and Edge is able to provide you 200 kbps. If you are using a mobile handset, so many times you will see that it will pop up that you are getting Edge as the network service, right? So the first important point is GSM and IS-95 are based for voice communication rate of around 10 kbps. So 10 kbps was enough for voice communication as well as small data services like SMS and all those things. But what happened is general packet radio service. What GPRS full form is general packet radio service, and enhanced data for GSM, that is called evolution Edge. So enhanced data for GSM evolution Edge were proposed with speed in the range of 100 kbps to provide low speed internet, right? So even if you are moving at low speed, you will get the internet service, email, etc. to users with mobile devices. So due to this GPRS and Edge, we are able to get this internet services, email with mobility. Even if you are moving, we are able to get this. So GPRS, you know that you will get GPRS service even when you are moving. And Edge is also when you are moving, right? So you will get these internet services. And Third point is that the increasing demand for higher data rates led to the development of this digital standard. What we observed that around 2000, year 1995 to 2000, what we observed that, so what we are data hungry, we want more data. So voice was good, we are quite happy with the 2G speech quality, 2G quality of service what we are getting through GSM. That's why GSM is still very popular, and IS-95, they were quite good for your speech communication. But a lot of requirements, a lot of services need data services, right? So we move to GPRS or Edge, or we move to 2.5 generation, 2.5G, and we are able to get this internet services with low mobility and data rate of around 100 kbps. But what led to 3G is that we wanted video telephony, we want video conferencing, right? We wanted that. At the end of 2000, around 2000, we all started feeling that we need a services where we can do this video calling, we can do the video conferencing while moving. We should have portable device which can be used for video conferencing, video calling, video meeting, a lot of things. So that basically, put a lot of emphasis on the development of 3G around 2000, year 2000, 2002, right? Now, coming to this 3G wireless cellular standards, I have just mentioned that there are two 3G generation, third generation. There are two services. One is the WCDMA or UMTS, another one is CDMA 2000, right? And you can see that these two standards are able to give you a data rate of 384 kbps, right? So that was almost 3 times data rate what was provided in 2.5G, right? But still, this 384 kbps was not good enough to do this video calling. Video calling was not possible because for video transfer, so for multimedia transfer, we need minimum 10 Mbps per stream. Keep in mind. So video wireless transmission, we need minimum 10 Mbps, right? So 3G was not able to, initially 3G was not able to give you video conferencing. Then we felt the need of 3.5G. We improved further. And 3.5G is what? We have, we have got a data rate between 5 to 30 Mbps. And we have two technologies. One is HSDPA or HSUPA, high speed digital downlink packet access. HSDPA means high speed downlink packet access, and HSUPA is high speed uplink packet access. Now you can imagine that you are getting now a speed of 5 to 10 Mbps. So 3.5G basically help us to give you video services, video calling, video conferencing and all, right? So that's why with 3.5G services, with 3G mobile headsets, we are able to do this WhatsApp calling, that is basically video calling. We are able to get this video conference you can do with 3G or 3.5G mobile handset. And so HSDPA and HSUPA was, the standard that was evolved from WCDMA or UMTS, and this 1X EVDO, that is advanced digital, this one, they evolved from CDMA 2000, right? So here the important point is that for video calling, for video conferencing on a wireless device, we need minimum data rate of 10 Mbps. And that was only possible when we moved from 3G to 3.5G. So you may wonder that what was the need from going from 3. Why they are from 3G to, why you are not going from 3G to 4G? Why the 3.5G in between came? The reason why 3.5G was required because we had to augment, we have to improve the data capability of 3G, that is 384 kbps. We have to increase it further to 5 to 30 Mbps. That was possible with this 3.5G standard. Now, coming to the 4G wireless cellular standard. So, point was that, fine, we have got this in 3.5G, we have got this services of, video telephony or video calling. But there are services like high definition TV. So because what happened that whenever this cellular standards evolved, the service, so a lot of services came into picture. A lot of industry that try to develop the services, new services to the customers with higher data requirement. So 4G was basically, the importance of 4G was that the need for 4G was that we want high definition TV, we want video gaming, right? We want multi-stream data transmission, multi-stream video calling, multi-stream video conferencing. For that, it was felt that 5 to 10 Mbps was not sufficient. What we need 100 Mbps. So need for 100 Mbps was, if you go backward manner, the requirement was 100 Mbps because we want multi-stream video transmission. So 10 Mbps was for single stream, but we need multi-stream video transmission. We need high definition TV. We had to increase the data rate and from 5 to 30 Mbps to 100 Mbps, 100 to 200 Mbps, right? So what we tried, we then started working on a lot of research, went through academia and industry, and we came with the fourth generation. And fourth generation has three important standards. First standard is LTE, which ensured 100 to 200 Mbps, but in general we assume that it's 100 Mbps. 4G, because LTE had a lot of additional features, we can go up to 200 Mbps, but the base LTE can give you easily 100 Mbps. Then 4G generation, fourth generation has another standard, that is WiMAX. It is also very popular in India. A lot of companies, they initially invested a lot in WiMAX. Mostly the BSNL has purchased the license of WiMAX services in almost all circuits in India, but somehow WiMAX services did not pick up. The reason was that LTE was so popular that WiMAX gradually it has, I can say that it is in a very bad shape, or there are very less users. Even if we find out there are very less users for WiMAX, but LTE, because LTE is also giving you 100 Mbps, LTE has more fluidity, better coverage. So WiMAX finally it has found a less acceptance compared to LTE. And finally, LTE Advanced. We talked about LTE Advanced. In a lot of places you see that LTE Advanced. So here we are talking about a speed of greater than 1 Gbps. So it is somehow we are moving towards LTE Advanced, or we are telling that it is 5G, right? Now this slide, I'm just trying to tell you that why different generations were required. Just to summarize, this summary of what we have discussed till now. So different generation, data rate supported, and applications. So if you keep that in mind, mostly for BTech students, that will give you a clear perspective that why these different standards was required and what they promise, right? So 2 to 2.75G was basically rate from 10 to 100 kbps, and they give you voice, low rate data, right? Finish. So that was in year 1990 to 2000. That was the year predominated by this 2 to 2.75G. Then came 3 to 3.5G. From 2000 onwards till 2013-14, we have this 3 to 3.5G, and they promised us from 300 kbps to 30 Mbps. And what are the applications we are able to get? Voice, data, video calling, video conferencing. So 3.5G is good enough to give you video conferencing. So, but 4G was felt because we need online gaming, we want to have high definition TV, we want multi-stream video transmission, and for that 4G promised us a data rate of 100 to 200 Mbps, right? Now, at this stage, you may feel that what more you want? Well, why we want a data rate of 1 Gbps, or why we want a data rate of more than 100 Mbps? Really, do we need a data rate of more than 100 Mbps? We'll see, yes, we need. Why we need? One reason is that there are, number of users. What we are increasing is exponential, right? A lot of users are being added daily. A lot of users, and even for a single user, there are multiple mobiles, right? So this challenge, because earlier there were few mobile users, but now there is a explosion. There is a explosive requirement by the users, by explosive number of data devices. We'll just see what 5G, why 5G was required. I'm just giving you a perspective. The question is that whether a data rate of 100 to Mbps, which are supported by 4G, and which has applications like online gaming, edge TV, and all the services of 3G. If 4G means what? Online gaming and edge TV is exclusive for 4G, but it can offer you all the services of what 3G and 3.5G can offer you, right? Now, I will just try to give you some next few slides are basically on LTE, that is 4G, basically long-term evolution. So, as I told you that in 2004, in fact, year 2004, 3GPP is a standardization body, third generation partnership project. So, worldwide, it is a standardization body which finalizes the standards for different wireless communication services. So, in November 2004, 3GPP began a project to define the long-term evaluation of universal mobile telecommunication system, right? And what they LTE talks about higher performance, backward compatible, and wide application, right? And it is what LTE is the next generation mobile broadband technology, that is from 3.5G we are moving to 4G, promises data transfer rates of 100 Mbps. So when we were talking about 3G and 3.5G, we thought 30 Mbps is good enough. Now we are talking about almost 4 times, right? 3 to 4 times increase in data rate from 3.5G to 4G. But at that time, we feel that in year 2004, we feel that what is the requirement of 100 Mbps? But now we feel that 100 Mbps is less, right? Based on UMTS 3G technology. And last point is very important. Optimized for all IP traffic. All internet protocol traffic, means all are packet switched. There is no circuit switch. So this 4G is optimized for all IP traffic. Now, so what were the major LTE radio technologies? Why LTE was feasible? Why LTE was possible? As an engineering student, as an engineering researcher, we should feel that what technology helped to move from 3G to 4G? What are the paradigm shift? What are technologies which made it possible that from 5 Mbps or 20 Mbps, we have come to 100 Mbps? One of the very important technique is orthogonal frequency division multiplexing for downlink. So LTE was used as orthogonal frequency division multiplexing for downlink. For BTech students, it is very, very important. For MTech students, it's very important to understand OFDM. OFDM was the backbone for 4G. I can say that without OFDM, 4G could not have been possible. Because downlink is more important, right? Downlink, we want to download more, right? Rather, uplink is just request for a service. Uplink is a small requirement. But downlink, we need more data transmission, heavy data transmission in the downlink. But OFDM is not suitable for downlink. So what we did, we uses single carrier frequency division multiplexes, SCFD for uplink, right? Another technical term is now single carrier frequency division multiplexes for uplink. Third point is very, very important. LTE uses multiple input, multiple output for enhanced throughput. MIMO was a game-changing technology. Due to MIMO only, we were able to get 100 Mbps. What we are doing in MIMO, we have multiple transmit antenna at the transmitter and multiple receive antenna at the receiver. This multiple transmit receive antenna help us to transmit at higher data rate. Another important point is that now you may feel that if you are transmitting 100 Mbps, a lot of power consumption will be there. So your battery, your mobile battery will drain out very fastly, right? No. And compulsory requirement is reduced power consumption. We cannot think of adding more data rates, adding more services with increased power consumption. We have to use the techniques which reduces power consumption. And thanks to this DSP, distance signal processing area, and VLSI, they are able to design a low complexity processors, signal processing processors, DSP processors, and VLSI architecture, which can, even if they are able to give high data rate, they are able to switch at a very high speed, but at the same time the power requirement is less. So development in wireless communication is highly, supported by advancement in DSP and advancement in VLSI technology. And finally, higher RF power amplifier efficiency. Because finally, whatever we are transmitting through the air. Your mobile device is simply doing things in the baseband. But finally, every mobile device has an antenna. This antenna, what it does, it converts a low frequency baseband signal to a very high frequency or RF signal, which is being transmitted to the air. And here, the power requirement is quite high when we're transferring a low frequency, low power signal to a RF signal with a very high power. So higher RF power amplifier efficiency is required. It means that less battery power used by the handsets, because handsets, one of the major constraints is the power amplifier, because they need a lot of power, DC power. Now, this channel, this slide I added purposely for the BTech students or MTech students, right? Because the biggest challenge, see, wireline channel and wireless channel. There are two types of channel. One is wireline channel, like your coaxial cable, your LAN cable. They all are wired channels. But now we are talking wireless channel. And there are two challenges in high-speed communication over wireless channel, right? The biggest challenge is inter-symbol interference and then frequency selective channel, right? These are two challenges because whenever transferred on a wireless channel, the channel multipath occurs, and this multipath results in inter-symbol interference. So that interference is not good. And similarly, the channel, if you are transmitting a high data rate, your channel will become frequency selective. It means that it will not pass all the frequency reliably, right? For some frequencies, it will be good, it will behave good, but for some frequency, it will behave very bad. So there will be deep fade, right? So we'll just see these two important concepts for wireless channel. So for example, I have shown you that you have a BTS tower is there from where you're transmitting signal to a mobile user, right? So this mobile user is there. Now, the transmission from the BTS to the mobile user has three paths. One is the direct path, and two are deflected path. One is being deflected by a moving vehicle, other is being deflected by a high-rise building, right? So what we observe that this wireless communication is a multi-path communication. It's not a single path communication, right? So I've just taken one path. So Y of t is what? S of t, that's a direct path from the transmitter to receiver, and then you have beta into S of t minus m, that is by the reflected path from the moving vehicle. And then the noise term. Noise term will be always there. That is additive white Gaussian noise, right? So Y of t is the output signal, means that is being received by the mobile receiver. ST is the input signal. ST minus m is delayed in m time input signal, and NT is the noise. And I have shown the graph also at the bottom. So signal received by the first path, that is signal received by the direct path, is a path which is received first because it takes the minimum time. But the delayed path will take longer time, and you can see that whenever it is delayed, these two paths have, their symbols are interfering, because what we want, the first path, that is direct path, this is sufficient. This path should be sufficient, but because we are transmitting a wireless channel, there will not be a single path, there will be multi-paths. So this multi-path, second path will be also received, and this second path is not aligned with the first path. So there is some overlapping portion. So this, suppose you are detecting a bit, it has interference from its own path as well as from the other path, or it has interference from own symbol as well as the previous symbol, inter-symbol interference. So this second signal is working as a interference to the first signal. The second path is acting as a interference to the first path, and this interference is called inter-symbol interference, because symbols are interfering. The symbols are not aligned. For a given signal, for a given symbol, we are getting energy from two different symbols. What we want? We want for a given symbol, it should get energy from the same symbol, but you are getting signal from the other symbol because they are overlapping. Two symbols are overlapping with the first symbol. So that's why we need equalizers in receiver. Due to this multipath, there will be intersymbol interference, and this intersymbol interference, to remove that intersymbol interference, we need equalizers, right? So I've just given you what do you mean an equalizer. So what we have done, just we have written the channel response in time domain. We have converted that into frequency domain. So, and what we have tried to find out, that we have tried to find out the channel impulse response or channel frequency response, because channel is behaving as filter. Always keep in mind, channel is behaving like a filter. So this it has impulse response of HCF, transfer function of HCF. So equalizer transfer function, that is, so at the receiver what we'll do, we want that equalizer is always at the receiver, and it has a transfer function which is equal to 1 by HCF. HCF is what? Is a transfer function of the channel. HCF is the transfer function of the channel, and this is basically 1 plus beta E minus J 2 pi f. So this filter, or this signal processing, so equalizer is basically signal processing. So this we have to do at the receiver to negate the effect of the multipath channel or wireless channel. So equalizers are must in the wireless communication receivers. Without equalizer, you'll have intersymbol interference, which is not good for the signal reception, which is not good for the reliability of the received signals. Now, next challenge is frequency selective fading. Right? So all of you, whether you're in BTech and MTech, you have to understand what you should know what is frequency selective fading, because frequency selective fading is one of the biggest challenges in 4G. It is one of the biggest challenges in 5G, right? Because whenever you are transmitting at a high data rate, your wireless channel will become frequency selective, right? What do you mean by frequency selective? Why this is so important, or why this is a biggest design constraint for wireless communication system? The reason is that you just see what we are doing. We are transmitting a single bandwidth. We are transmitting a clean pulse, right? It's transmitted single carrier signal. Multipath, due to multipath, what will happen? You just see the receive signal. Right hand side is the receive signal. So receive signal will have distorted receive signal. Receive signal is not a clean pulse. It has a distorted. The pulse is distorted, and there are some points where the signal power is reduced tremendously, and these points are called defades. These defades are not good, because defades is what? The signal is totally lost, or in other words, in digital communication, there will be multiple errors. Your receive signal can have 50% in error, 50% bits are in error, right? And this is called frequency selective fading, right? Now, how to take care of this frequency selective fading? Here, you get the help of Ofdm. Ofdm is a technique which takes care of frequency, because whenever you transmit at higher data rate, the channel will get bigger, because frequency selective, they will have multiple defades. So more than 50% or at least 50% of your received signal will be in error. So that's why I have written in the red color. It may be useless for increasing transmission power, because transmission power is not going to help you, right? Because your signal is distorted and you have multiple defades. What you have to do? Solution is multi-carrier transmission, or in other words, Ofdm. Now we'll go through a few slides on OFDM. Because OFDM, in the beginning I had told you, OFDM is a technique for 4G or LTE. LTE was possible only due to, if anybody asks me, I will say that this is one of the most important technology for 4G to be successful, right? That is OFDM. It's a multi-carrier transmission. We are not transmitting a single carrier. We are transmitting multiple carrier. So OFDM is basically orthogonal FDM. FDM everybody knows, frequency division multiplexing, but it's orthogonal. Orthogonal frequency division multiplexing. What it means that all those carriers, there are multiple carriers, but they will not interfere with each other, right? What do you mean by orthogonality? That the peak of each signal coincides with trough of other signals. Now you just see that there are in total 7 carriers. There are 7 subcarriers and they are transmitted in parallel. Or I can say that all the 7 carriers are transmitted simultaneously. We are not transmitting single carrier. What we have seen that in single carrier case, the transmission becomes frequency selective and we have multiple fades if you are transmitting a single carrier. Now what we are doing, we are transmitting multiple subcarriers and that too simultaneously. And we say that they are not interfering with each other, or mathematically if they are not interfering with each other means they are orthogonal. But physically what is happening, what orthogonal means that, if you see that whenever the first carrier F1 is at the maximum value, because whenever we take the decision whether it is 1 transmission or 0 transmission, we sample at the middle of the carrier. So whenever we are sampling or whenever we are taking a decision whether it's 1 or 0, whether this pulse represents a 1 and 0, at that time all the signals, all 6 other carriers have 0 value here. The amplitude of other signals are 0. See, for F2, only when you take at the middle, when you sample this at the middle of this F2, in that case, what we see that all other signals have 0 value here. Physically, it means that, what do you mean by physically? What is mean by orthogonality? The peak of each signal coincides with trough of other signals, right? So they are orthogonal. And the condition is that this, how they can be orthogonal, how you can ensure that peak of each signal coincides with trough of other signals. The condition is simple condition. If you think that the condition should be that the difference between F1 and F2 should be 1 by TS. Yes, TS is a symbol period, right? TS is a symbol period. TS symbol, after each symbol time, it will repeat itself, right? After TS symbol time, it will repeat. So if the difference between F1 minus F2 is 1 by TS, we can ensure that whenever F1 is at the peak, all other 6 signals will have the minimum value or 0 value. This is the condition we are keeping for orthogonality. Now, this is a very interesting slide. FDM is what? Frequency division multiplexing, or FDMA. We know that FDMA is the technique what we use in the first generation, or FDM. So FDM, what we are doing, we have a frequency band and we have 3 users. So what we are doing, we are giving 3 users different bands, and between 2 bands, we are giving the guard band, right? This band is basically the guard band. We are not giving the continuous bands. We are giving the guard band in FDM or FDMA. But when you are coming to OFDM, what we are allowing? We are allowing that this should now overlap. There is no reason, right? So here we have 3 subcarriers, but here what we did, that we ensured that they should not overlap. And what we are doing, we are giving the guard band. But here what we are doing, we are allowing them to be we are allowing them to overlap by using orthogonal frequency bands, orthogonal frequencies, and in this process, what we have done, we have added 2 more users, because now we can overlap. But they are overlapping, but they are orthogonal, right? So in place of 3 users, now we have 5 users. Or in place of 3-bit transmission, now we have 5-bit transmission. So that's why we say that OFDM is a strictly efficient method. Although we are allowing multiple signal transmissions, multiple carrier transmissions, but because they are orthogonal, they are spectrally efficient. This is very, very important point to keep in mind. OFDM is spectrally efficient because we are, although we are allowing multiple subcarriers, but they are orthogonal, and in the same band of frequency, we can transmit multiple subcarriers, so they will be more spectrally efficient because we are able to add more users, or we are able to transfer more data. Initially, either you can transfer 3 datas, now you can transmit 5 datas, right? Now, the conclusion is that why OFDM? Why OFDM? Because high data rate symbols are converted into low data rate symbols by serial to parallel converter to cope with inter-symbol interference, which is one of the biggest challenge in wireless communication. Second is that better than single carrier communication over feeding channel, because we are able to take care of frequency selective channel, that is a deep feed, right? Now we'll just see that that's why OFDM was important in 4G. Now just see that what we are doing in OFDM. So we see that we are converting serial to parallel, right? We are doing serial to parallel. And so what 4 bits, if you are using single carrier, you are transmitting 4 bits per second, right? Single carrier. But what we did, 4 bits per second means what? In 1 second, we are transmitting 4 bits. Now what we are doing, we are converting this single transmission to serial to parallel. Now we have 4 transmission. That's serial to parallel conversion. And each transmission, we are transmitting 1 bit. But we are keeping the data rate same. Here in 1 second, we are transmitting 4 bits. So each bit has 1/4 second duration. But here, what we are doing, we are transmitting 4 bits in 1 second, but each bit has 1 second duration. So we are increasing the time span, time period of the bit. But total bit rate is same. And why we are doing this? Because this will take care of your inter-symbol interference. Now you say that how it will take care of the inter-symbol interference? I will just show how it is helping you to take care of inter-symbol interference. Just see this slide. Transmitter and receiver, inter-symbol interference for high data rate transmission. So you are transmitting 1010 at the receiver, you are receiving 101 with some delay, tau. Tau is the delay. Whenever this delay is more than TB, TB means bit duration. This TB is the bit duration. Whenever this tau max, this tau maximum value of tau is greater than TB, then inter-symbol interference occurs. Because whenever it is more than TB means what? That symbol will appear in the next symbol. The 2 paths. Just remember the example of 2-path transmission we have discussed. So whenever the delay is more than TB, it means that that symbol will appear in the next symbol. So this will increase the inter-symbol interference. How to avoid that? We have to increase the bit duration. If you increase this bit duration, then all the paths will be received in the bit duration TB itself. It will not go to the next symbol. If you increase the symbol duration, then what will happen? All the multipath components will be receiving that duration only. They will not go to the next symbol. It means that we are trying to avoid the inter-symbol interference. And the last line is very important. Why this is important? Because when you are going for high data rate transmission, the bit period will reduce. See, if you are transmitting at 10 Mbps and now you are transmitting at 100 Mbps, so TB is reduced by 1/10. So TB is reduced by 1/10. So inter-symbol interference will be quite high. So for high data rate transmission, TB decreases, so occurrence of ISI increases. So one of the effective way to take care of intersymbol interference is that increase the bit duration, increase the symbol duration in time domain, and that is what we are doing here. Here we are increasing from the bit duration is 1/4 second. Now here the bit duration is 1 second. We are increasing it to 1 second. So all the multipath components will be received in this bit duration only. They will not go to the next symbol, and we are able to take care of the intersymbol difference. Any doubt up to this point? Now, very interesting point I am telling you. This Ofdm was invented something around 1960, 1960, right, for these cable operators and all. But it was not very popular. Even in 2000 onwards, we felt that Ofdm is a good technique, but it is very difficult to realize. The reason was that in Ofdm, we are transmitting multiple subcarriers, right? We are simultaneously transmitting multiple subcarriers. It means that we need, suppose, data serial to parallel. So now you have n parallel paths. N parallel path means that you need to have n number of oscillators, and then they are finally summed up. Right? They were transmitted simultaneously. So we had to design so many oscillators. Designing oscillators is very difficult, right? These many oscillators are transmitter and n number of oscillators are receiver, right? And this should be orthogonal. This should not. So it means that delta f should be always equal to 1/ts. F1 minus F2 should be 1/ts. Then they will be orthogonal. But you know that hardware components are always not 100% reliable, right? If temperature increases, the frequency what they are generating, it will change. Even the aging effect will change the frequency it is generating. So if you remember the oscillator properties, if you study the oscillators in your BTEC, you remember that oscillators are hardware components, right? Even if you have two chips with the same oscillator, you are designing two oscillators, and we are making the hardware for two oscillators, same oscillator designed for frequency of 100 megahertz, and you take 10 oscillators, they will differ by some amount. One thing, temperature changes, the 100 megahertz will now be 100.001 megahertz. There is some change in the frequency there. And we observe that if there is change in frequency, they will not be orthogonal. So problem was bank of oscillators required. I'm talking about hardware oscillators or electronic oscillators. Very hard to maintain frequency separation delta f, because they need to orthogonal means delta f should be 1/ts. That was the problem. That's why this Ofdm was not popular, although it was proposed in year 1964 or 65. For the 40 years, it was isolated. It was not talked about. No research. But gradually, what we did, just concentrate here. This is not at all required. This is not feasible. This is not going to make our life easy. It is not required. Cross means is not required. What we did, we converted this bank of oscillators by endpoint IFFT, inverse fast Fourier transform, or inverse IDFT, DFT, discrete Fourier transfer, IDFT, inverse discrete Fourier transform, right? I hope all of you understand if you are in third year and final year, right? FFT and DFT, right? Frequency transfer, digital frequency transfer, right? So this bank of oscillators can be replaced by IFFT, right? IFT will generate orthogonal subcarriers easily. Now I'm giving you homework. Try to prove that how IFT can be used to realize orthogonal subcarriers. How IFT can generate orthogonal subcarriers. But because IFT can do this, Ofdm came into picture in 4G from 2000 onwards. And the biggest, I can say, biggest, propellant of 4G is this OFDM and implementation of OFDM using this IAFT and FFT realization. At the transmitter, we are using IAFT. At the receiver, we are using FFT, right? And then we have other, I have already told you that if you are using this OFDM, we have improved spectral efficiency, reduced ISI effect and multipath component. It is good at against frequency feeding channels. These all advantage of OFDM. Coupled with that, now we can realize this OFDM with IAFT and FFT. That made our life very easy. And that was the reason that 4G became so popular. And that is the reason that we are still thinking, very important point here to make out is that we are still thinking for OFDM in 5G. 5G till date, everybody in 5G standard, all the world, gradually we are accepting that for OFDM will be technique for 5G also. OFDM will be an integral part, very important point for 5G also. So understanding of OFDM is very, very important. And I have tried to make you understand that how OFDM is important, how OFDM is able to take care of this intersymbol interference and the frequency selective channel, how OFDM can be realized using IAFT and FFT. And finally, this is your final block diagram. This is a functional block diagram of OFDM, right? Foundation for LTE and Wi-Fi. Wi-Fi also uses OFDM. OFDM is used in multiple places. Just observe this. If you are in third year and final year, you will be able to understand what we are doing here. Just give few minutes, few seconds to this, and then I will explain you. Well, so what we are doing in the left side, if you see, so this block diagram is basically simplified OFDM waveform synthesis for a transmitter. So we have a data, we do this coding, error control coding, and then we are doing this modulation. Then this is converted to serial to parallel. Then we are doing IAFT. IAFT is the foundation to OFDM synthesis. Then we are adding cyclic prefix to this. Then we are doing this windowing and filtering. Then finally it is sent to the RF. Finally transmitted as a RF signal, right? So there are. So just see the third block. Third block, what we are doing? We are just what we discussed in previous slides. Data transmitted via closely spaced narrowband subcarrier. And what this IFT does, IFT operation ensures subcarriers do not interfere with each other, right? Inverse fast Fourier transfer or inverse discrete Fourier transfer operation ensures subcarriers do not interfere with each other. IFT is operations which generates subcarriers which do not interfere with each other. This is the IFT operation. Then what we are doing, we are adding cyclic prefix. What do we in cyclic prefix? So what we do helps maintain orthogonality despite multipath fading, right? Even we have multipath fading destroys the orthogonality of the wireless transmission, right? So we have to see that they are still orthogonal. So what we are doing, we are doing the cyclic prefix. And then finally, we are doing this windowing and filtering. So windowing, why it is required? Because whenever we're transmitting a waveform, when you are transmitting a sync waveform in the time domain, right, it will have multiple side lobes, right? So to remove the side lobes, we are doing windowing to remove the out of band emission, right? We don't want that our transmission should be out of band emission. For that, what we're doing, we are not transmitting. We cannot transmit a square pulse, right? Because the square pulse is not realizable by real filters, practical filters. What we do, we send RRC pulse, raise cosine pulse, or some pulse shaping we are doing here, right? We are doing some filtering operation so that transmitter waveform after windowing, we are doing some windowing also so that the out of band, beyond that band, there will be least power, right? This is called out of band emission. Now conclusion. Now we are concluding here, right? It's all about OFDM because OFDM is very important. That's why I've given you that much time. Although I'm running with time, but anyway, this if I am able to convey the concept of OFDM to you, I think my purpose of giving this lecture will be sufficient, right? So what are the advantages of OFDM? Spectrally efficient, robust in multipath environment, coexistence with current and future systems, simple equalizer. We have seen that equalizer will be very simple. Disadvantage, right? Disadvantage, some spelling mistake. I don't know why it has happened. Disadvantage, high sensitivity to, there are three important disadvantages. Now the problem is that you always keep in mind no system design is perfect. It will have some advantage, but it will have some serious disadvantage also, right? So disadvantage is that they are highly sensitive to inter-channel interference, sensitive to frequency, clock, and phase offset. Time domain signal has a high, relatively large peak to average power ratio. So these are three important challenges, and I can tell you that a lot of research in the past 20 years has put to tackle these three challenges, right? Still in 5G, when we are moving to 5G, these three challenges we are doing a lot of research because OFDM is a de facto standard. OFDM we have to use, but OFDM comes with these three important disadvantages, right? So we have to see that how we can overcome this high sensitivity to inter-channel interference, sensitivity to frequency, clock, and phase offset, and how we can take care of the high PAPR, right? And finally, to motivate you to learn OFDM technology is that just see the applications of OFDM. OFDM can be found in standards A02.118GH. Basically, this is a wireless LAN standard. Then you have this WiMAX standard A02.16A, and then finally A02.2G, that's wideband, this ultra wideband standard. It is being used fixed as well as it is used in fixed or wireline systems like ADSL. This now, can you ever thought that why this same twisted pair cable which is coming at your house, right? That same telephone set what we are using for voice communication, same twisted pair you can use for high-speed broadband connection at your using this wireline communication, right? And one of the reasons is this ADSL, asymmetric distance subscriber line, and OFD is used in ADSL also. That's fixed broadband communication. We are using this twisted pair cable for in our house for voice communication. Same wire is used for giving you broadband communication of 50 Mbps, 40 Mbps, which was only designed for a speech communication of maximum 64 kbps. And finally, different mobile and radio standards like digital audio broadcasting, digital video broadcasting, Hyperline 2, WiMAX, physical layer architecture of 3GP, long-term evolution, and 4G, right? Now, so what I will do, because we are running short of time, I will just try to give you the glimpse of fifth generation. Now we are ready with understanding of 4G and what is the key technology in 4G, that is OFDM. Now we'll see that what are the fifth generation challenges, why fifth generation challenges are very different from what we observe in 4G, right? Although it will have challenges what 4G has faced, right? It will be challenged by the frequency selective nature of the channel. It will be challenged by inter-symbol interference. It will be restricted by the wireless channel, but it has some more challenges, right? Because fifth generation will give you so many new services which has its own challenge, which has its own requirement on the network, right? Now, see this figure, see slide, the contents and the right side, I have given a curve, right, a figure, a picture of that. So challenge is that, or I can say challenges or requirements, 5G requirements, I can say, right? The requirement is basically challenge, 5G requirement is challenge. What we need in 5G, that we need 1 to 10 Gbps data rate in real network, right? From 100 Mbps, we are moving to 1 Gbps or 10 Gbps. Second point, 1 millisecond round trip latency. So in 4G or LTE, the latency is 10 milliseconds, round trip latency. But what we target, what is the requirement of 5G is 1 millisecond. Third is high bandwidth in unit area, fine. Enormous number of connected devices, we know that. Almost 100% coverage for anytime, anywhere connectivity. So coverage should be 100%. Second last point, reduction in energy uses by almost 90%. Now you see what stringent requirement we are putting on this energy consumption. It's to reduce by almost 90%. Now you can imagine. You can design system, it is working fine, but if the energy consumption, power consumption more, there will be no taker. There will be no taker at all. And finally, we talk about this low power consumption because we are using portable devices. Right hand side, what I have shown you is very important. What we are expecting in 5G, 10,000 times more traffic. 10,000 times more traffic. 10 to 100 times more devices. This comparison with the 4G I'm talking about. Latency is 1 millisecond. 10 years battery life for machine-to-machine communication, because machine-to-machine communication, it is not possible to replace the battery, right? So we want 10 years battery life. Machine-to-machine communication is ultra low cost. For fixed users, we want 10 Gbps data rate. And for low-end data rates, we need minimum 100 Mbps. At the same time, we need ultra reliability. Now, I'll just see you a slide where the requirement I have put in the red colored 1 millisecond round trip latency. This requirement for 5G is putting the biggest challenge to system designers, design engineers, how to implement that. How you can ensure 1 millisecond round trip delay. Just I will show you. Then you realize this has one of the very important challenge. Just see that. LTE, that is moving from 10 millisecond to 1 millisecond, latency I'm talking about. LTE requires minimum 10 millisecond. 10 millisecond means what? In mobile devices, all signal processing, all everything what we are doing in mobile devices, equalizer, Ofdm, then windowing, filtering, then RF, we need 4 milliseconds. Minimum requirement is 4 milliseconds. When we are coming to the BTS side, 4 milliseconds is required at the BTS. Then 1 to 2 milliseconds is required in the core network. And for internet, that's 5 to 10 milliseconds if in the same country as the customer. If customer is the same country, we need 5 to 10 milliseconds. So on an average, we need 10 millisecond LTE minimum. But when we're moving to 1 millisecond, what we have to do? 5G service requires some 1 millisecond. Now, it means that this mobile processing, which was 4 milliseconds earlier, now it should be done in less than 0.5 millisecond. And whole processing of the BTS, core network, internet, they all need to be implemented within 0.5 millisecond. Now you can imagine that how difficult, and it is one of the biggest challenges. And till date, we are not able to get 1 millisecond. We are able around 4 to 5 milliseconds. 5 milliseconds, I can say. A lot of companies they did a lot of R&D, a lot of technology was developed, and right now we can say safely that we can get a round time trip latency of 5 milliseconds, but not 1 millisecond, right? This is an important slide, which because now we are in 2020, so I thought I will give you some idea about what wireless 2020 and beyond outlook. So just have a look on this. On the top, I'm writing enhanced mobile broadband. So these are 3 services which are we are thinking in 5G. The first one is the enhanced broad, because we all are using mobile. So that's the first one is enhanced mobile broadband, EMBB in short we write. So and the other is the machine type communication, because 5G is one important application that we are talking about machine to machine communication. That to massive, not 1 or 2 machines, thousands, lakhs, machine type communication, right? So first one is enhanced mobile broadband communication. What we want here for cellular operators, For cellular communication, for cellular users, most of us are basically we are going to use this enhanced mobile broadband service. Most of us, right? Machine type communication is for the industry people, for the application oriented one. But for us general users, this is basically we are interested in enhanced mobile broadband. And what we want? Very high data rates in terms of 1 Gbps and more, high spectral efficiency, high mobility, low PAPR in uplink, simplified receiver design, high densities. These all are the requirements on enhanced mobile broadband. And what I'm telling right now here is that this all requirement is 10 times or 100 times what we think in 4G, right? Now, coming to this machine type communication, it has two parts. One is IoT. Most of you know that about IoT, and IoT is a very important application of 5G, right? So if IoT, what are the requirements? IoT is that we are talking about orthogonal transmission, right? We have been orthogonal transmission. But orthogonal transmission is not going to help you in IoT or machine type communication. Non-orthogonality. High spectral efficiency is required, low compressivity is required, low PAPR is required. These all high spectral efficiency, low compressivity, low PAPR is always required. But we cannot go for orthogonal transmission in IoT. We have to go for asynchronous transmission, minimum OOB, out of band radiation, right? These are the requirements for IoT. What are the examples of this? Sensor networks for smart grid. We are talking smart grid sensor networks. Sensor network, important example of IoT. That smart cities and homes, intelligent transport systems. These all are the examples of IoT, right? That those IoT requirements which can be supported by 5G, right? Now I will come to a very interesting thing: ultra reliable and low latency. We have used the term ultra reliable and low latency. What latency is required? Some millisecond latency. Immune to Doppler, means even if you are moving at 500 km/h, it should not, there will be Doppler frequency, right? Doppler spread. We know that when we are moving, the received signal frequency will change. So it's very difficult to maintain orthogonal transmission. Low complexity. And what are the applications? Tactile radio. Or very important, very interesting application is autonomous self-driving vehicle, right? All of you see that Tesla and all, so many companies they are coming with autonomous self-driving vehicles. Now you can say, imagine that if you're designing a self-driving vehicle, autonomous self-driving vehicles, the response time of that vehicle should be less than millisecond. Otherwise, there will be collisions, right? There will be a lot of accidents. This should be ultra reliable. The reliability of communication should be ultra reliable, right? And these all are possible only when we are talking about 5G. 5G will support all this, either enhanced mobile broadband or machine IoT, like smart grid, smart cities, intelligent transport systems, or tactile radio, tactile internet, or autonomous vehicles. These are the few applications which require the support of 5G. Last slide, right? Here I am trying to highlight two important things. How this 5G will be realized, right? So 5G will be realized in two ways. One is the evolution path, and other is the new radio access technology. That means new radio access technology. What evolution means? What it will be evolved top of 4G or LTE advanced, right? Whatever 4G technology we have developed, based on that we have to add more features, we have to add more technology, and we have to see that is evolved as the 5G service provider, right? So the first point what I have written is the evolution of LTE advanced will continue beyond in a backward compatible manner with the goal of improving system performance in the bands below 6 GHz. Here we are trying to keep our services of below 6 GHz. So evolution path will be for below 6 GHz, right? So what we are doing, we are trying to evolve this LTE technology to the 5G technology, right? Second point is that it is also expected that at least a part of 5G requirements can be met by the continued evolution of LTE Advanced. So 5G, whatever requirements of 5G is there, part of that should be made possible by the advancement of 4G. So that our 4G network, which we have invested a lot, which has itself an advanced technology, that can be utilized. And that can be utilized, that can be used as a part of 5G by adding more technologies on that, right? The second track, that is a new radio access technology. The second track is commonly known as the new RAD track in 3GPP, which is not limited by backward compatibility requirements. It means whatever technology we are developing in new radio access technology will not be compatible with 4G technologies, right? They will totally different one, paradigm shift. No relation with the 4G technologies, right? So the second track is commonly known as the new radio access technology track in 3GPP, which is not limited by backward compatibility requirements and can integrate breakthrough technologies to achieve the best possible performance. We are talking about breakthrough technologies which will make this 5G possible. And those breakthrough technologies are millimeter wave, massive MIMO, full three-dimensional MIMO. So millimeter wave and massive MIMO are the two breakthrough technologies which will be a part of new radio access technology, and these two technologies need not to be backward with compatible with the 4G, right? And there are technologies which will be added on this 4G so that 4G can evolve, it can be enhanced to be part of 5G, and they will be around 6 gigahertz. But the new research technology will be in millimeter wave. It means that it will be in the range of more than 25 gigahertz, right? This new radio research technology we are targeting around 25 to 27 gigahertz right now, right? So because the time is up, I hope I try to cover the fundamentals of 4G, and I have tried to create interest to the participants that what 5G challenges are and how 5G is realized, what are the two tracks, and how we can do for them, right? Thank you. Any questions?
Yes, sir. Thank you for your nice presentation. I think from
Thank you, Ashraf.
participant side, I think 2 questions are there. So please go through the chat box.
Okay. Chat box.
Okay, there are
Yes.
2 questions. Question 1 and question 2.
So first question is, I'm able to see. In LTE Advanced, do we get the data rate speed beyond 1 Gbps? No. LTE Advanced, although the target was greater than 1 Gbps, but LTE Advanced never achieved 1 Gbps, right? 1 Gbps still we are talking about in 5G scenario only. In 5G only 1 Gbps is possible. That too for a very short range communication, right? For short range communication using millimeter wave, we are able to get 1 Gbps. But LTE Advanced, we were, although the target was 1 Gbps, but we were never able to get the value of 1 Gbps in LTE Advanced. And the second question is that without guard band in Ofdm, is there any chance of interference or crosstalk? A very good question, because we are not giving guard band in Ofdm. We are allowing the Ofdm to overlap. But the problem is that about the interference is that's why I told you that this is one of challenge of Ofdm. So whenever there is carrier frequency offset, what we told that F1 minus F2 should be 1 by TS, right? So the separation frequency should be 1 by symbol time. Whenever there is a mismatch of these two, either due to multipath channel or either due to the Doppler spread, they will not be orthogonal. They will start interfering with each other, and we have interference, right? I hope I have answered the questions.
Okay, so thank you for your nice presentation. So now we have come at the end of the session. So it is my pleasure to thank you, the esteemed speaker, Professor Pritam Kumar. Thank you, sir, for your enlightening the talk on wireless communication. You have discussed the 1G, 2G, 2.5G, 3G, 4G, and then finally the challenges in the 5G. So thank you, sir, for your nice presentation. Hope the participants will be benefited by your nice presentation. And we hope that your association with NIT Silchar, especially in the Department of Electronics and Communication Engineering Department, will continue in near future also. Thank you, sir.
Sure, sure. Thank you, Ashraf, and thank you, other faculty colleagues. I'm seeing Dr. Devinder Gujar, Pravina is there,
Yes, sir.
and I'm really happy that first time I'm interacting live, or I'm presenting something on in NIT Silchar, and I always look forward to be part, or in any way I can be associated with NIT Silchar. I will be very happy. Thank you, Dr.
Sure.
Ashraf.
Sure, sir. Sure, we shall do this. With your suggestion will be helpful to our department. Okay, sir. Thank you.
Sure, sure.
Thank you,
sure.
sir. Thank you, sir.
Thank you, Pravina. Thank you. Thank you.
The announcement for the participant. Next session will start from 2:30. Okay, we have another sessions in the afternoon, so please join at 2:30. Okay, thank you.